Okay guys, this is the first video for Chapter 4, which covers the stoichiometry of chemical reactions, and we are going to focus on this first section involving writing and balancing chemical reactions. So here are the two learning objectives. We are going to focus on this first learning objective here, just simply trying to understand chemical equations and balancing them, and then this second objective involving the total ionic and net ionic equation, we are going to save that for a future video. So chemical reactions involve the rearrangement of atoms within a substance. So you have a transformation in the identity of one set of substances to form a new set of substances. And that is depicted in the chemical equation, which represents this transformation. So here's an example. We have sodium metal reacting with chlorine gas to produce sodium chloride as a solid. And so the parts here on the left of the arrow are called the reactants. The parts on the right-hand side are called the products. And the arrow means these species react to form, or sometimes you would say these reactants will yield these products. Another part of the chemical equation are the numbers that you see in front. These are called the stoichiometric coefficients. Oftentimes you will see phases listed in chemical equations, and sometimes you'll see reaction conditions listed both above or below the arrow. So here's an example of the chemical equation. We can interpret chemical equations in different ways. So here I have another chemical equation. So we have nitrogen reacting with hydrogen to form ammonia gas. We can interpret this at the molecular level, where one molecule of N2 reacts with 3 molecules of H2 to produce 2 molecules of ammonia. Or we can interpret the chemical equation at the macroscopic level using moles. So we can interpret this equation to mean 1 mole of nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia gas. If you convert those moles to grams using the molar mass of each species, you can also represent the chemical equation in terms of masses as well. Chemical equations can be used as conversion factors. For example, let's suppose that you have a given amount of nitrogen. You may want to know how much ammonia can I produce from that amount of nitrogen. So you can convert from grams or moles or molecules of nitrogen to grams, moles, or molecules of your product, ammonia. Or you can go the other way. Suppose you need to make a certain amount of ammonia. You can ask yourself, what amount of nitrogen and or hydrogen do I need in order to make that much ammonia? And you can also convert between reactants. So I can convert from nitrogen to hydrogen, or if I had multiple products, I could convert between two different products. Okay, so these are the types of games that we are going to play in this chapter. This is what stoichiometry is all about. However, in order for these calculations to be performed, we must have a balanced chemical equation. What that means is that the chemical equation satisfies the law of conservation of mass, which would require that you have the same number and type of atoms on each side of the chemical equation. I'll go back to this equation. Notice here you've got 2 atoms of nitrogen, and you have two ammonias. Okay, so there's a balance between the number of nitrogens on the reactant side and the number of nitrogens on the product side. Likewise, on the reactant side, you have 6 hydrogen atoms, and you're going to have 2 times 3 equals 6 atoms of hydrogen on the product side. So this is a balanced chemical equation with respect to both the number and type of atoms on each side of the reaction. So we need to be able to take an unbalanced reaction and balance it. You are not allowed to adjust the subscripts within any of the chemical formulas because that would change the identities of the substances that are reacting. It would be a different reaction if you did that. So you have to leave the subscripts alone. However, you are allowed to adjust the stoichiometric coefficients that appear in front of chemical species. When you're balancing an equation, you often need to recount the atoms on both sides of the equation to check whether or not they're balanced. And the way that I like to balance equations is by inspection. And I have essentially two rules. The first rule is you have to choose an atom to start with. And the atom that I like to pick is one that appears in only one chemical species on each side of the reaction. That's usually your best bet to balance the reaction. And then the second rule is you need to recount the atoms often as you're trying to balance it. And so it's kind of like a little game that you have to play where you make a little change to one of the stoichiometric coefficients and then you need to figure out what's balanced and what's not balanced. At the end, you're going to have a set of stoichiometric coefficients. If you can, you need to reduce those down to the smallest integer ratios. And that's usually the accepted stoichiometric equation for whatever reaction that you're considering. And always, always recount at the end, especially on an assessment, to make sure that you've got the balanced equation. So we are just going to do some practice balancing. So I'm going to show you how you balance chemical equations by inspection. And so we'll start with this first one here, H3PO3. I believe this is phosphorus acid. Reacts to form phosphoric acid and phosphorus trihydride. And so we see that the phosphoruses are out of balance, the oxygens are out of balance, and so are the hydrogens. Okay, so we need to balance essentially each atom. Which atom do we want to start with? Well, my suggestion is that you start with the atom that appears in only one species on each side. And if you look here on the product side, both the phosphorus and the hydrogens appear in both species. So I recommend that you don't mess with those, at least not at first. Since oxygen appears in only one species on the products and one species on the reactants, let's start with the oxygen. Here you've got 4 oxygens in the products and 3 oxygens in the reactants. The way you balance this is by taking that 4 and putting it in front of the phosphorus acid and put the 3 in front of the phosphoric acid. So you'll do a 4 and a 3 there. And now that you've made that change, you want to check. You know that you've balanced the oxygens. You're going to have 12 on each side. But you want to check everything else. So you've got now 4 phosphoruses on this side. You've got 3 plus 1 gives you 4, so phosphorus is balanced. What about the hydrogens? You've got 12 on this side. Here you've got 9 plus 3 more. That gives you 12. So this reaction is balanced now. Part B is another fairly easy one. We've got calcium reacting with water to give us calcium hydroxide and hydrogen. Okay, so we want to look to see what's out of balance and what's not. It looks like calcium is balanced. However, the oxygens are not and the hydrogens are not. Why don't we start with the oxygens, since oxygen appears only in water on the reactants and only in the calcium hydroxide on the product side. We see that we've got 2 oxygens here and only 1 there. So if we put a 2 there in front of the water, let's see how that changes the situation. Calcium is still balanced. We know that the oxygens are now balanced. What about the hydrogens? Well, now we've got 4 coming from the water, and then we've got 2 plus 2 more, 4 on the products. So this reaction was balanced fairly easily as well. Let's look at part C. Part C is a lot more complicated, and so let's handle this one with care. Let me get the reaction going. So we've got iron 3 sulfate reacting with ammonia and water to yield iron 3 hydroxide and ammonium sulfate. Okay, so what do we have going on in this reaction? Well, we see that the ions are not in balance, right? We've got 2 on the reactants and only 1 on the products. The sulfurs are out of balance as well, as are the oxygens and the nitrogens and probably the hydrogens too. So there's a lot going on here in this reaction. So we want to figure out what atom do we want to start with. And you've got a number of choices here. I'm going to go ahead and start with the iron because it appears in one species in the reactants and in only one species on the products. So it's a good choice. And it's pretty easy. So we've got 2 irons here and only 1 there. So we're going to put a 2 there in front of the iron 3 hydroxide. Well, now we need to figure out what we want to do next. Nitrogen might be a good choice, but sulfur might be a good choice as well. Sulfur is kind of interesting here because it's paired up with oxygen in the sulfate in both the reactant side and on the product side. And so we could actually try to balance at the level of the sulfate. That might be helpful. And so we see that we've got 3 sulfates here on the reactant side and only 1 sulfate on the product side. So what if we put a 3 right there? Now we have 3 sulfates. Okay, so iron is still balanced. The sulfates are now balanced. That includes both this sulfur and these oxygens are balanced. So we don't want to go messing with these now if we can help it, because that's going to throw things off. What's left to balance is the nitrogen, and we still have a little bit of oxygen left over to balance probably, and the hydrogens, of course. So why don't we take a look at the nitrogen first, since nitrogen appears here in the ammonia and it appears here in the ammonium. We see that we've got now 2 times 3, 6 nitrogens, and only 1 nitrogen on this side, so it's fairly easy to put a 6 there and balance those nitrogens. What about the leftover oxygen? Not these oxygens, because those have been balanced already. But what about the 3 oxygens here? Actually, it's 3 times 2 gives us 6 oxygens right here, compared to just 1 oxygen within the water. So let's take and put a 6 in front of this water. And now what we want to do is hope and pray that we've got the hydrogens balanced, because there's nothing left for us to mess with. And so let's figure out if the hydrogens are balanced. So we've got 6 times 3, that's 18 hydrogens on the reactant, plus 6 times 2, that's another 12, for a total of 30 hydrogens on the reactant side. What about on the product side? We've got 3 times 2, so that's 6, plus we've got 2 times 4, 8 times 3, 24, for a total of 30. So like magic, the hydrogens ended up being balanced, which is always fun. So this is now the balanced reaction for this one. I am going to leave the other 4 reactions here for you to try out on your own. Some of them are easy and some of them are a little tricky, so why don't you give it a shot. This is something that you need to be pretty good at in order to do stoichiometry. So checking to see that your reaction is balanced is always the first step. On the next example, here we're taking a description of the reaction in narrative form, and we're turning it into the chemical equation and then balancing it. So this is also a useful skill. You need to be able to read a description of a reaction and turn it into the chemical equation. So here we've got molecular nitrogen is reacting with oxygen to form dinitrogen pentoxide. And so here you need to know your nomenclature, right? In 2O5. And so we'll check, is this reaction balanced? Well, the nitrogens are balanced. However, the oxygens are not. And so here what I'm going to do is I'm going to illustrate what I call the fraction trick when you're balancing. We've got a monoatomic species here that's got 2, or not monoatomic, we have an elemental species here that's diatomic. So we have an even number of oxygens on this side, but we've got an odd number of oxygens on the product side. One way to balance this fairly quickly is to take the oxygen and multiply by 5 over 2. Now that seems kind of weird to do, but if you take 5 divided by 2 and multiply by 2, it does give you 5. Now, we don't like to have fractions in our stoichiometric equations, and so what you need to do is to take the whole reaction and multiply by 2. That'll get rid of the fraction, and then the reaction will be balanced. So we've got 4 nitrogens and 4 nitrogens, 10 oxygens, and 10 oxygens on that side. I call that the fraction trick. Let's go ahead and do this, this next one. So we are going to do the decomposition of ammonium nitrate. So we get a little practice with our nomenclature. Ammonium nitrate to form molecular nitrogen, that's N2, molecular oxygen, O2, and water. So they even give us a hint, balance the oxygen last. And the reason why you want to do that is because oxygen appears in 2 species over here and only 1 species there. We want to choose the atom that appears in only 1 species on each side. And it looks like you could do nitrogen or hydrogen. I'm going to start with the nitrogen. We've got 2 nitrogens here and only 1 there. Oh no. Nitrogen's already balanced, so I don't need to do anything with nitrogen. So I guess we do need to start with hydrogen in that case. So we've got 4 hydrogens here, and we've got only 2 there. So we should put a 2 in front of that. Nitrogen's already balanced. The hydrogen's balanced. So the last thing to do is to balance the oxygens. And the place you want to balance the oxygens is right here in front of that species. Okay? So I'm going to put an X right there. We want to find that coefficient. So I'm going to say that 3 on the reactant side needs to equal 2 times X plus 2. Now you just solve for X. So 3 minus 2 is going to give me 1. We're going to get X equals 1/2 out of that, so we get to use the fraction trick, multiply the entire equation by 2, and we can check to see if everything's still balanced. So now we've got 2 times 2 is 4. 4 nitrogens there. For the oxygen, we've got 2 times 3 is 6. 4, 5, 6. And for the hydrogens, we've got 8 and 8. So this reaction's balanced. So I think that's the last one I wanted to do in this video, so I'm going to go ahead and stop it right here.